So previously we've looked at buffers and how a buffer works. And now what we want to do is we want to look at how do we actually calculate the pH of a buffer solution. Now reminding us that a buffer solution is a weak acid and its conjugate base, or a weak base and its conjugate acid, right? So we have significant amounts of each of those. So we're going to be able to, once we know how much we have of each of those things, calculate the pH knowing how much of a weak acid or a weak base we have present in the solution. Also being able to calculate how our pH changes as we add in a strong acid, and how our pH changes for this buffer, and how we add in when we add in a strong base. Specifically focusing on what kind of neutralizing reactions do we have that are going to neutralize our base or acid when they're added into solution. Now, when we're using a buffer and identifying how the pH is changing or what the pH is, we have the ability to use a magnificent tool, the Henderson-Hasselbalch equation, which is telling us that we have the pH of our solution is equal to the pKa of whatever weak acid we have in the buffer, so our buffer weak acid. And to that, we're going to add the log ratio of the concentration of our base to acid, or the mole ratio of our base to acid. We notice we can use these interchangeably, and we'll talk about why we would possibly choose one versus the other. So let's first look at our first buffer that we have here and talk through some of the applications of this. So what we're told is that a buffer was prepared by adding formic acid and potassium formate. So here we have a weak acid. It's good to investigate what kind of solutes we have, a weak acid. And then this is a salt that contains potassium and the formate ion present in solution. Just for simplicity's sake, I'm going to write HA and A minus now for those to simplify rather than having to write the whole structure out every single time. And we're told that this was done in a 2-liter solution where we have a certain concentration of our formic acid and a certain concentration of the formate ion with our potassium formate. So important thing to notice is that we have a pretty good amount of each of these, or similar concentrations of each of those. And that is a good hint to us that this will be a buffer solution, even though we are already told it's a buffer solution, but that's because we have similar concentrations of our acid and our conjugate base. Okay, not the same, but similar enough so that way we can see that we're going to have similar amounts of those and significant amounts of those. So the first thing we want to do is identify just the pH of our buffer. So it is a buffer. We can use pH equals our pKa value plus the log of, again, we could use the molarity or mole ratio. Well, since we already have these in molarity, let's go ahead and just look at the ratio of our concentrations of base to acid and be able to identify our pH there. So here we would have our pKa, that is for our formic acid, and we can go to a table, we can find the pH, and then the pKa, which would be 3.74 for formic acid. And now we can go ahead and plug in the information we have. Our pKa, 3.74, plus the log of our concentration of our base, 1.25 molarity, and then the concentration of our acid, 1.50 molarity. We would get a pH of 3.66. Now again, this is a buffer, and we are able to utilize the Henderson-Hasselbalch equation. But maybe if we wanted to connect this back to what we've done many times before, and thinking of, can we do this setting up a Rice table? So reaction, initial, change, and equilibrium. So again, we have our reaction. And a lot of times what we want to do is we want to take reactant 1 and reactant 2 and add them together. So we would think, oh, maybe it's just formic acid, potassium formate. But one thing that we want to observe with a buffer is that we do have the presence of a product for our acid ionization reaction of our formic acid. So for example, we're not going to look at that, but if we just look at the normal acid ionization reaction of formic acid, we're going to get H3O plus and the formate ion. So what this is telling us is that we actually start with some amount of our product and some amount of our reactant. So it's not necessarily that these two things are reacting together, but what we can say is that we have what we call this common ion that is present in our solution, which is going to cause our equilibrium to be shifted in a way that wouldn't be like that if we started with no potassium formate. So again, now we have our reaction. We want to write our initial change in equilibrium for those. So we start with 1.5 molarity of our formic acid. We start with 1.25 molarity of the formate ion, and we didn't directly add in any hydronium. Water is a pure liquid, so we don't include that in our K values and our expressions. Because we start with no H3O+, what that helps us identify is that must mean it's going to increase in concentration to get to equilibrium, and that means that our concentration of our reactant is going to decrease. So we end up with an expression for our reactants and our products here. Now, as we would always do now, is we're going to go ahead, right, and plug those into our Ka expression, right, these variables that we have for our reactants and products. So our Ka is going to be our product concentration divided by our reactant concentration at equilibrium. And we know the Ka value for our formic acid is 1.8 times 10 to the negative fourth. Again, we go to a table and we can find that. And we plug in what we have for our concentrations here. Now, if we look at this, we could plug in and we notice that we could solve for x. There's only one variable, but this is not an algebra class. We want to think, can we maybe simplify this a little bit? And we take a step back and we see we have a small K value here. And we're starting with a lot of product already, 1.25 molarity. And so what that lets us know is that we're not going to form that much more. So that tells us our X value is going to be small because we do have this small K value and we already start with a lot of product. So I could go ahead and see, can we make this assumption that these numbers of 1.25 and 1.5 are effectively going to be the same as if we included that minus X or if we didn't. And what that does is that simplifies our math to be 1.25x divided by 1.5 equals our K value. And now we can go ahead and solve for our X value, and we're going to get 2.16 times 10 to the negative fourth. And again, we say, okay, well, that's pretty small relative to our 1.25 or 1.5, so it makes sense that we can make that approximation. Now we go back to, we're trying to identify our pH. We know that that is our hydronium ion concentration. And so now we know our hydronium ion concentration, we can calculate our pH to be the negative log of that. And we would get a pH of, thankfully, the same pH that we originally got. So we notice we have the ability to choose either one of these. We could look at a Rice table, or we could use our Henderson-Hasselbalch equation to quantify our pH. I'm going to advocate for us to use this one because it simplifies it, but also we'll see when we deal with buffers and start to get more complicated buffers, it's easier to just simplify what we're looking at. And if you go into a biochem course, a lot of times this is the main way that they focus on calculating pH for a buffer. So we did that first step in quantifying the pH of just a buffer. Now let's go on and move on to thinking about, well, what happens if we add an acid? So HCl, and we think, what is HCl? HCl is a strong acid, is one of our strong acids. So we're going to add 25 milliliters of 10 molar HCl to 1 liter of our buffer solution. So again, reminding us our buffer solution is 1.5 molarity acid, 1.25 molarity conjugate base. Now what we notice here is that we're adding 2 volumes. So if we're adding 2 volumes, what that's going to mean is that we're going to need to account for dilution, or if we simplify this a little bit and thinking we still have a buffer solution, instead of looking at molarity, let's go ahead and look at moles, because moles will not change upon dilution. We'll still have the same moles of solute. So again, if we're going to use our volume and our concentrations, reminding us that our molarity is moles over volume, and specifically in liters. So if I want to calculate the number of moles, that's going to be our molarity times our volume. So if we go ahead and do that for each of these, we would find because we have 1 liter, we're going to have 1.5 moles of acid, 1.25 moles of base. So now, even though we've added some volume to our solution, we're not going to change the moles of acid that we have or moles of conjugate base unless we think of a reaction happening, which we're going to look at now. So again, now we have the moles of these, and we're going to remind ourselves that one of the ways that a buffer works is it neutralizes the added, in this case, because we're looking at an acid, H3O plus. And we think back to the fact that we have a pretty good amount of acid and a pretty good amount of its conjugate base. Well, if we're going to neutralize that H3O plus, it probably would make sense for us to think of it as reacting with our base there. So we're going to neutralize the H3O plus by reacting it with that conjugate base. So it's going to transfer a proton from the H0 plus to A minus, give us our acid, and now we've neutralized it, and now we're just left over with our base here. Now, what does this do to our solution? How is this going to influence our pH? What we notice is that this is going to decrease the amount of our base and increase the amount of our acid simultaneously. And how much is that increase and how much is that decrease? That is directly related to the moles of hydronium that we add, because that's going to be our limiting reactant. If it's not our limiting reactant, we've blasted out our buffer and we no longer have the ability to neutralize that H3O plus. We're not dealing with a buffer solution. But if we do have a smaller amount of acid than we had of our original base, we'll notice that that's going to effectively be our limiting reactant. And we're going to decrease by some amount of that base and increase by some amount of that acid. How do we account for this when we're doing our calculations? And how do we account for this in thinking about the amount of base and acid that we have? I believe the simplest way to do it is just start by writing out our Henderson-Hasselbalch equation that we originally started with. So we originally started with pH equals our pKa, 3.74, plus the log of, and this is where we're going to use moles now, because then we don't have to deal with this idea of dilutions. So it's going to be a log of 1.25 mole of our base, 1.5 moles of our acid. Now this is, again, all of this right here is before we have our added HCl. But now, as we just talked about, we're going to increase the amount of acid and decrease the amount of base. So what we mean by that is because we're going to increase the amount of acid, we're going to add to the acid. And because we're going to decrease the amount of base, we're going to subtract from the base. Now, how much are we going to add or how much are we going to subtract has everything to do with how much H3O plus we have. Now, again, if we look at our volume and molarity of our HCl, that would tell us that we're going to have 0.25 moles of HCl that is added. So again, here, this is the moles of our HCl, which is also the same as the moles of H0 plus that we add, because we know that HCl is a strong acid. It completely ionizes. And so what that means is that effectively now we have 1 mole of A minus left over. Run out of room here, and we have 1.75 moles of acid now present in our solution. So we basically have shifted some of that base to become the acid. And because this is a weak acid-base equilibria, it's not going to generate a whole bunch of change in our H3O plus concentration. And so we should see maybe that our pH doesn't change very much. And so we'll find that now our pH is 3.50. Now, if we compare that versus the original pH of 3.66 for our original buffer, we notice a couple of things that should happen, right? We have a decrease in pH, right? And that would make sense because we've added a strong acid. In addition to that, that decrease in pH is small because we've had the ability to neutralize that strong acid by reacting it with our conjugate base. So we notice those two things, number one, and number two, the pH decreases, but that's also a small pH change because we've added it to this buffer that has the ability to neutralize that hydronium by reacting it with our A minus. Now, maybe if we look at this let's compare this to, well, what happens if we didn't have a buffer? So here we say, well, what happens if we add this same amount of HCl? So here we have 0.25 moles of HCl to 1 liter of water. So we notice in water, there is no buffer. There is no significant amount of conjugate acid-base conjugate pair for a weak acid or a weak base. Because of that, all of that HCl will still be in solution. Now we've noticed that we've gone basically from 25 milliliters to 125 milliliters. And so because of that, we're going to see this big change of our pH that we would see for the water. If we think of our water, our pH is 7, right? We have a neutral solution. And now we have a pH that's going to be much lower because we have not neutralized any of that H3O plus by adding it into our solution. And so here what we look at, if we want to think of how is our pH going to be affected, we need to first find the concentration of our HCl. So that's going to be 0.25 moles in our now 1 liter plus our 0.025 liters, because we've added these two volumes together, and we're going to find that we have a concentration of 0.244 for our solution here. So that's going to be the concentration of H3O plus, or also the concentration of HCl. And we know that those are the same because it completely ionizes. Well, now if we know our concentration, we can calculate our pH as the negative log of that, 0.244 molarity for our H3O plus. And so we're going to get a pH of 0.613. And so we see here is that we've gone from a pH of 7 all the way down to a pH of 0.613. And that is a huge pH change. And that's because we don't have any base there to neutralize that acid that would be present in our solution. So we notice that that's the importance of thinking of a buffer that we have here for this solution. So that's adding just this acid to water. There is no buffer there. So let's now go to the flip side. What happens if we add a base to a buffer solution? Again, we have our 1 liter of our buffer. I'm just going to stick with our mole amounts that we had originally talked about. 1 mole of our acid, 1.25 moles of our base. Again, that's because we have our 1 liter solution. To this, we're going to add sodium hydroxide. And we remind ourselves that sodium hydroxide is a strong base. It's a metal hydroxide that is soluble in water. We want to figure out how our pH changes. So what's our new pH once we've added this base to our buffer? Again, reminding us that our original buffer pH was 3.66. So let's think about how it might change. So if we think conceptually about what we just noticed with an acid, what we should see is an increase in pH, but a small increase in pH with the addition of our sodium hydroxide. And again, reminding us when we're looking at adding our sodium hydroxide, we are going to be neutralizing that sodium hydroxide if our buffer is going to work correctly. So if we have our sodium hydroxide, effectively we have sodium ions and hydroxide ions. And this is going to be the species that's going to really change our pH if we can't neutralize it. But if we do have a buffer, what we see here is that our buffer is going to neutralize that hydroxide by either reacting it with our conjugate base or a weak acid. So if we have this base here to neutralize it, we're going to have to react it with an acid. So we're going to have hydroxide reacting with our acid, and that's going to give us H2O. And A minus, you notice we're ignoring our sodium ion there. That sodium ion is just simply a spectator ion, just hanging out, watching what's happening. So now we have our reaction here. What can we make for an observation? We can say this is going to lead to a smaller amount of our acid. While we're neutralizing that acid, we're also producing more A minus. And again, how does that correspond back to the amount of hydroxide that we have? That's going to be related to the amounts of hydroxide that we add into this, because again, our sodium hydroxide is going to be a limiting reactant. It's going to limit how much of our acid we have and how much of our base we produce. So like we did before, let's go ahead and start out by just writing out what our buffer looked like before we added in our base here. So 3.74 is our pKa. The log of the ratio of our base, 1.25 moles of base, 1.50 moles of acid. And now that we would see, and we look at this, we'd see we're going to increase the amount of base. So we're going to say that's going to be an increase in our base there. And then we are going to decrease the amount of acid. So that's going to decrease the amount of acid. And that makes sense. We're adding a base, so it should neutralize the acid or base that we would have there. And if we're thinking of what kind of solution, we add a base, it's going to neutralize our acid, and it's going to produce more of our conjugate base. And so that's why we're thinking of both of these, decreasing the amount of acid, but also increasing the amount of base. How much is that going to be? That's going to be related to the number of moles of sodium hydroxide that we have. Again, if we look at our molarity and volume, we'll find that that would be 0.285 moles of sodium hydroxide that we add. Here again, this is the moles of hydroxide or sodium hydroxide that we have reacted away to get rid of our HA, but also produce that much A minus. Go ahead and plug this into our calculator, and we find that our pH now is 3.82. Again, we compare that back to our original pH, and does this match up with our observations that we predicted we should see? That we should see an increase in pH, but it should be small. And we noticed, yes, it's pretty small. We've added a lot of base, but we only increase our pH by 0.16. So it's very small increase in pH than we would see if we just added it to maybe water here. Question, and so then now we see we have an increase in pH, but it's very small, and we're going to change basically the amounts of our acid and conjugate base that we would have present in solution. So now that we have the ability to see the addition of an acid or a base to a solution, I'm going to let you work on number 5 on your own to practice that. And so if we think of, we add 30 milliliters of 9.5 molar sodium hydroxide to 1 liter of water, can we calculate the new pH of this solution? So why don't you go ahead, pause the video, and answer what you would say would be the concentration, the new pH that we would get, and then we'll come back and you can see how I work through it. So now hopefully as you're thinking about this, we're adding it to water, and you had a chance to do this on your own. If I want to find the pH, I either need to know the POH or I need to know the hydronium concentration. That's going to get us to our pH. Well, we're adding a strong base to solution, so I would find that our hydroxide concentration is going to be equal to the number of moles of hydroxide. Again, that's from our volume and molarity here, divided by our volume that we'd have. Again, we have a 1 liter solution, and now we've added 30 milliliters, or 0.030 liters of a solution to that. So our total volume is 1.03. So we would get a concentration of 0.277 molarity. Well, we could go ahead now and find our POH, negative log of 0.277. And we would find that our POH would be 0.558. So pretty high POH, which makes sense because we have a lot of base. But our pH is going to be 14 minus our POH, which will be 14 minus 0.558. And we would find that we would get 13.442 as our pH. So we've gone from a pH of 7 all the way up to 13.442. This is, again, a huge increase in pH because we have nothing there to neutralize or react away the added base that we have. Now we've compared an acid and a base being added to a buffer and being added to just water. Now let's look at it in a different way. Now let's say we wanted to make a specific buffer. Okay, so we want to make a buffer by adding some amount of an acid and some amount of its conjugate base. Again, here we have a salt that contains the conjugate base. So we're going to get Na plus F minus, and we add it into 1.5 liters of a solution, and we know that we have a specific pH. So our goal pH that we want to find is 3.50 for our buffer that we would have. We want to find out how many grams of sodium fluoride must be added to make this solution with the specific pH we want if we know the concentration of acid that we have. So why don't you go ahead and pause the video and do this one on your own, see how far you can get, and then come back and see how I work through it. So now that you had a chance to work through this and think about it on your own, again, we're looking at a buffer. And whenever I look at a buffer, I always jump straight to the Henderson-Hasselbalch equation and look at what kind of information do I know that's going to be helpful for me as I'm looking at my solution here. So here we have a buffer, and we know that our buffer is going to have a pH of 3.50. That's what we want. We know the identity of our acid and conjugate base. So that means I know the pKa of HF is 3.17. I know the concentration or moles also of HF that I have. And we see here, if I need to find out the mass of NaF that I need, I'm going to probably have to figure out how much fluoride I need to give me that specific ratio of F minus to HF to give me my desired pH. So now, again, we're looking at the mass of NaF. So if I want to get to the mass of NaF, from that, I first want to maybe find the moles of NaF that I need. So instead of looking at molarity ratio here, we're going to look at the mole ratio, because maybe that will kind of save us some time as we're working through this. So again, we have our pH of 3.50, our pKa 3.17, plus the log of, we're going to call it X moles of F minus, and we have 1.125 moles of HF. And again, we used our volume and our molarity to find out what our number of moles of HF we have. So we go ahead and do some quick algebra. So we get 0.33 equals the log of X over 1.125. And again, just to remind us, the tool that we have to get rid of a log is we take 10 to the power of that log, and we do that to both sides. So we're going to get 2.138 equals X over 1.125. We multiply that 1.125 across, and we would find our X equals 2.41 moles of F minus, which is also the same as the moles of NaF, because we know that we have a 1-to-1 mole ratio between them. So if I want to find my mass, I'm going to go ahead and use our molar mass that we have right here, 41.99 grams of NaF for every 1 mole. And so we would find that we would need 101 grams of NaF needed to be added into the solution to give us our desired pH based upon the amount of hydrofluoric acid that we already started with. So hopefully this video gives us a good introduction into thinking about the calculations that relate to buffers. And again, I highly recommend getting used to using the Henderson-Hasselbalch equation, because this is really helpful for us as we're analyzing buffer solutions and how those pHs are affected by the addition of a strong acid or a strong base, or how we make these buffers.